welcome back. I hope you had a good break. In the break, I had a couple of minutes to think, and I realized there was one more thing that I wanted to say about the vibronic structure of the NV center before moving on. But let me briefly recap. In the first 45 minutes of my talk, the first half, I tried to introduce you to the electronic structure of the NV center and give you some sense of what these energy levels actually correspond to and why you have spin-dependent intersystem crossings between the spin triplets and singlets. And in the last slide, I introduced the notion of the vibronic states associated with each of these electronic levels. That is, the quantized motion associated with ionic displacements when the electrons are in each of those energy levels. And the one thing that I wanted to mention that I forgot to mention is that this vibronic structure of the NV center that leads to this very low fluorescence within the zero phonon line can be viewed as maybe one of its less than optimal features. And the thing that I wanted to bring to your attention was that this is one area where people are looking for other defect centers that might have more favorable properties. And indeed, defect centers such as the silicon vacancy center in diamond have been shown to have zero phonon lines that account for nearly 80% of their overall fluorescence. This because they have a structure that has inversion symmetry. That is, you can reflect everything through the origin and get the same structure back, which can lead to these very low couplings between electronic transitions and ionic vibrations. And so this is one of the areas where one might look for an improvement to the NV center. Okay, so with that one addendum, let me go on now to talking about the resonant optical transitions of the NV center that is exciting directly between these ground triplet states and the excited triplet states, how they are probed and what they can be used for. So a typical way to explore the resonant optical transitions is through what's known as photoluminescence excitation spectroscopy. What that means is that you take a laser that's close to resonance with the zero phonon line, and you sweep it in frequency across the zero phonon line, across all of these transitions, while monitoring the fluorescence that comes out broadband, that is typically in the phonon sideband. And what you see when you do one of these experiments is typically a set of very sharp lines that are detuned from each other by a few gigahertz. This for a specific NV center in an electronic grade sample. And I'd like to draw your attention to a few features of these resonant optical transitions. The first feature is that these lines are quite narrow. If they were limited by the lifetime of the excited state, which is about 12 or 13 nanoseconds, you would expect them to be something like 15 megahertz wide. And this has been almost seen in a couple of select electronic grade samples. And this allows you to do things like see Rabi oscillations on the optical transitions, that is, coherent population oscillations between one of the ground states and one of the excited states on nanosecond timescales. I'd also like to draw your attention to the fact that these transitions are spin selective. Here I've labeled these transitions by the symmetry of the excited state to which they correspond. And for example, this transition EX, that has to start in the ms=0 state, as you'll recall from our discussion of selection rules and also from energy considerations. And so this transition from ms=0 to EX can only occur if the spin is in ms=0. Whereas the transition, say, to E1 and E2 can only occur if the spin is in ms=±1. And of course, that's coming both from selection rules and from the energy selectivity, that is, the precise frequency of your laser can only drive resonant transitions. But if you look carefully at this spectrum that I'm showing you, might be coming to the conclusion that I lied to you in the first half of the talk. Because in the first half of the talk, I was trying to motivate the energy level structure from symmetry, and one of the requirements of symmetry is that E energy levels be degenerate. And if you look carefully, you'll notice that EX and EY, these two ms=0 energy levels, do not appear to have the same energy experimentally. And indeed, this is because the strain in the diamond can break the C3V symmetry. It can shift and mix these levels. And so spectra will depend on the precise strain and local electric fields that the NV center feels. and every NV center will have a slightly different fingerprint of its resonant optical transitions. So let's talk a little bit more about strain. The effects of strain have now finally been mapped out and understood, although it was one of the things that complicated attempts to understand the resonant optical spectra of the NV center. In zero strain, the story that I told you is correct. The NV center does have C3V symmetry, and the E levels are degenerate. However, if you have strain that's perpendicular to the symmetry axis of the NV center, then you break C3V symmetry, and levels that would nominally be degenerate with each other start to split and to mix. If you didn't see that animation, I'll run it again. This is what happens as a function of transverse strain, wildly exaggerated. These levels shift, and actually these run through each other, leading to spin mixing. And in the limit of very high strain, you end up in this situation where you have essentially two orbital states that correspond to states that are, I guess, along and in some sense orthogonal to the strain direction, that are each like a spin 1 triplet with different orbital states. Conversely, if you have strain that is parallel to the symmetry axis of the NV, it shifts all of the energy levels together. And so it wouldn't show up as a splitting of the levels, simply as a change of their energy levels. Now, this is one of the challenges to working with NV centers, that no two NV centers are exactly alike if they have different strain configurations. However, you have some control over what's going on here, because electric fields behave in much the same way as strain. And so this can be viewed as one of the features of the NV center resonant optical transitions, that it has electric field tunability. By fabricating gate electrodes on the surface of your diamond, you can apply voltages that will shift the electronic levels and shift the frequencies of the resonant optical transitions, and you can even tune the EX and EY transitions to degeneracy, tune it to the zero strain point if you have enough degrees of freedom of control. So this electric field tunability can be an asset if you want to tune two NV centers into resonance with each other. However, it can also be a liability in the sense that if you have electric field tunability, you have electric field sensitivity to any sources of electrical noise in your sample. Experimentally, this is observed as spectral diffusion. Here, this is one of those sharp resonant transitions observed in photoluminescence excitation, and you'll notice that the frequency jumps every time one of these green arrows happens. These green arrows are repulse pulses, 532 nanometer repulse pulses, in between the sweeps of the red laser over the zero phonon line. And these jumps are associated with spectral diffusion caused by changes in local electric fields induced perhaps by ionization of charge traps or recombination of charge traps associated with the green excitation. So it might seem like there's a really obvious solution here. Don't apply green light. However, there's a reason for these repulse pulses. And the reason is if you just apply red light to the NV center, it ionizes. Just applying resonant excitation to the NV as a function of time, you see the fluorescence drops on a time scale of roughly milliseconds. What's happening here is that when you resonantly excite the NV center, you're exciting the negatively charged state from its ground state to its excited state, from which another red photon can ionize it, taking one of the electrons up into the conduction band. This deposits you in the ground state of the neutral NV center, which, as I mentioned briefly in the beginning, has an optical transition at higher energies. And so the resonant excitation just doesn't have enough energy to touch it. And the system gets stuck in the neutral NV. To bring it back, you can apply green excitation that has enough energy to excite the NV0, and furthermore enough energy to bring an electron out of the valence band and repopulate the negative charge state. So it might seem that this combination of electric field sensitivity, ionization, and spectral diffusion induced by the green repump is a really kind of a problem for the NV center. However, there are several approaches that have been taken to overcome it. One is to use voltage feedback to stabilize the transition. Another is to switch from using 532 nanometer repump which is off resonant for the NV0, to using a 575 repump, which resonantly addresses its transitions and can be used at much lower powers and thus leads to less spectral diffusion. A particularly successful approach has been to repump until resonant. That is, you keep trying until the NV center comes to the frequency you want, and then you do the experiment. And lastly, there's been a lot of work very recently in material science and surface science to try to stabilize the environment of the NV center so you don't get these electric field fluctuations even in the presence of green excitation. And there's select natural samples and a few samples that have undergone implantation and annealing that have shown very narrow line widths with very little spectral diffusion by having very noise-free environments. Okay, so with these caveats of some of the features and challenges associated with the resonant optical transitions, let me talk a little bit about how you can use them to access the spin degree of freedom. One of the simplest things that you can do is optical pumping. That is, if you'd resonantly drive a transition into a state that has a relatively high probability for its spin to flip, then if you keep the light on that transition, eventually the spin will flip and it'll all end up in the other spin state from which it can't be excited. And this can be a very efficient way to prepare the spin with about 99.7% fidelity. Conversely, if you look at optical transitions that don't have a high probability of spin flip, for example, the EX and EY transitions, these are very nearly cycling transitions. They can undergo hundreds of optical cycles before you get a spin flip. And as a result, you can use them for resonant detection of the spin. The idea is very simple. If you send in light that is resonant with one of these transitions, you expect to get many photons if the spin is in ms equals 0, and none if it's in ms equals plus or minus 1. And this can be used to detect the spin in a single shot, again at low temperature, with about 95% fidelity. I should emphasize that all of these resonant optical techniques, they only work at low temperature. These direct resonant techniques for preparing and detecting the spin aren't the only kinds of games you can play at low temperatures with the resonant optical transitions. Another type of approach you can take is a dispersive approach, where you tune your transition slightly away from one of the energy levels. This can allow you to do things like observe Faraday rotation, changes in the polarization of the light that you send through, conditional on the spin state, or optical Stark effects, that is, rotations of the spin around its z-axis induced by the optical excitation. A particularly versatile configuration that's been used by a number of experiments are lambda-level configurations. These are configurations like what you get in zero strain for the ms equals plus and minus 1 states. I'll remind you what that looks like. Let me just shift those two levels apart. I'll remind you that, for example, transitions from the ms equals plus and minus 1 ground states to the A2 excited states have circularly polarized selection rules in a lambda configuration. That is, where the two ground states are connected to the same excited state. This is one way to achieve a lambda configuration. It can also be done by using electric or magnetic fields to tune the excited state levels to a situation where one of them is very highly spin mixed. Regardless of how you obtain this lambda level configuration, it's a very versatile one for manipulating and controlling the spin state. For example, you can use a lambda level configuration to do coherent population trapping by applying resonant light on both of these transitions with phase-locked lasers. What happens when you're exactly on 2-photon resonance with these two lasers is that you optically pump the spin into the superposition of the ground states that no longer interacts with the two lasers. This is observed as a reduction in fluorescence associated with the 2-photon resonance condition. In other words, it optically pumps the spin states into a coherent superposition that's set by the amplitude and relative phase of your lasers. And this allows you to do things like prepare and detect the spin in an arbitrary basis. A lambda level configuration can also be used to drive Raman transitions of the spin, where simultaneous application of these two laser fields induces 2-photon oscillations between the ground state spins. So this is a little taste of some of the all-optical techniques that are available with the NV center at room temperature. And I hope it gives you some picture of the toolbox that we have for optical access to the spin. That is preparation, detection, and manipulation. However, all of this really only works well if you're below about 10 Kelvin. And it's natural to ask why. It's natural to ask what happens as you turn up the heat. Well, as you turn up the heat, one of the things that happens is the line widths broaden. Those nice narrow line widths, they get broader, they get smaller, and eventually they become unobservable. The polarization selection rules also disappear. Mysteriously, there's an electron spin resonance signature that suddenly pops up around 100 Kelvin that wasn't there at low temperatures. We now understand what's going on here. What's going on is that as you raise the temperature, you're inducing phonon processes that start to average over the two orbital states within the excited state. This motional averaging effect takes you from a strain-dependent, very coherent set of excited states at low temperature to a strain-independent state at high temperature where your orbital state is essentially rapidly averaged between the two possibilities by thermally excited phonons. And so at high temperature, you have what looks like an orbital singlet where the spin transition from ms equals 0 to ms equals plus or minus 1. And indeed, it's that spin transition that's observed in ESR at high temperatures, but not at low temperatures. Nevertheless, there's still some uses for the optical transition at room temperature, because the spin dependence of the intersystem crossing remains. And this leads to the possibility for room temperature spin preparation and detection. When you excite at room temperature, the zero phonon line is completely washed out, and so it's much more efficient to excite into the phonon sideband, typically with green light, because it's both inexpensive and right at the peak of the phonon absorption sideband. And from the excited state, the different spin states have different lifetimes and different probabilities to couple into the singlets. Once they've coupled into the singlets, they relax very slowly on a time scale of a few hundred nanoseconds, so that when you turn on light at room temperature, you'll see different fluorescence traces depending on the initial spin state. In particular, if your spin started off in ms equals plus or minus 1, you'll see this gray curve where you get fast population of the metastable singlets and then slow recovery out of them. Whereas from the ms equals 0 state, you get a much slower approach to equilibrium in populating the singlets. And so there's a transient fluorescence signal that lasts a few hundred nanoseconds that can be used to gain some information about the spin state. However, I should emphasize, in contrast to the resonant optical techniques at low temperature, this is not a very high fidelity measurement. You don't get a trace that looks like this in a single shot. In a single shot, you probably get, on average, about 1/10 of a photon. The signal-to-noise ratio is quite low. Excuse me. Furthermore, as this process approaches equilibrium, you get a net polarization into the ms equals 0 state, but it's not 99-point-something%. It's somewhere in the range of 70 to 90%, depending on the sample and the NV center. Nevertheless, although these techniques are not as high fidelity as what can be done at room temperature, the fact that it operates as what can be done at low temperature, the fact that it operates at room temperature and even above, and can be done with a very simple, literally a green laser pointer, makes it particularly appealing for sensor applications. So I hope between my discussion of the resonant optical and non-resonant room temperature techniques, you have some idea of how exactly we can use optical techniques to access the spin of the NV center. And so let's move now to understanding a little bit more about that spin physics. A typical experiment to observe optically detected magnetic resonance or optically detected electron spin resonance with the NV center might look a bit like this. You'd have your sample, this little blue thing here, mounted up at the focus of a microscope objective that couples in your excitation light, and you'd be monitoring the fluorescence that comes out and hits a photon counting detector through the same path. If you aligned everything very well, you might get maybe 300,000 photons per second. At the same time, you can apply microwave magnetic fields to your sample to flip the spins. And you expect that under this continuous wave optical excitation, the spin will polarize into the brighter state, the ms=0 state, so that when your microwaves hit resonance, it will drive you into the darker ms=±1 state, and you'll see a dip in fluorescence. And indeed, this is what would be seen. You'll see dips in fluorescence associated both with the ground state spin transitions and with transitions within the excited state. They have slightly different splittings, about a factor of 2 different, but they have approximately the same G factor. That is, they both have a G factor of approximately 2 because they're both in an effective orbital singlet state. And I draw your attention to a couple of features in this diagram. The excited state level anti-crossing at about 500 Gauss, and the ground state level anti-crossing at about 1,000 Gauss. These are the points at which the spins, the ms=−1 state crosses the ms=0, and similarly in the ground state as you turn up the magnetic field. Now, most of the experiments with the NV center are done with the ground state because it lives a lot longer than the excited state. And there you would want to turn off the excitation while you apply a microwave pulse sequence to manipulate your spin. So you would have a pulse of light to polarize the spin, some microwave pulse sequence to manipulate it, and another pulse of light to detect the spin. And within the ground state, we can start thinking about what is the Hamiltonian for the spin. Certainly it'll have this zero field splitting and a Zeeman effect, but it actually also has, I should mention the zero field splitting, it's temperature dependent, minor detail, but it can be useful. But there's also some interactions with electric fields that are equivalent to interactions with strain. So this can be used in sensing applications as well. However, they're very weak. They're much weaker than the Zeeman interaction at the level of about 20 Hertz per volt per centimeter for the electric field sensitivity. In addition to just the electronic spin Hamiltonian, we should consider its interactions with nearby nuclei. This encompasses both the host nitrogen nucleus, which can either be a I=1 nitrogen 14 or an I=1/2 nitrogen 15 that are coupled by an anisotropic hyperfine tensor with typical elements in the range of 2 or 3 megahertz. It can also encompass interactions with nearby carbon-13 spins, which exist with about 1.1% isotopic probability in natural isotopic purity diamond. And these coupling coefficients, they depend on the lattice site of the carbon-13. It can range from 130 megahertz for the nearest neighbor carbon-13s down to, well, as low as you can see. And that really depends on the coherence time of your electronic spin. You can observe the hyperfine interactions by zooming in on one of these ODMR peaks. For example, in the situation where you have one nitrogen and one carbon-13 spin, and you zoom in on one of these transitions, you might see a hyperfine structure that looks like this, where the triplet splitting is associated with the I=1 nitrogen nuclear spin, and the doublet splitting is associated with the I=1/2 carbon-13. And indeed, this is an opportunity to use optics not just to address an electronic spin, but actually to address several nuclear spins. Recent techniques have extended this to the point where you could think about optically addressing something in the range of 5 to 10 nuclear spins. But how exactly do you do that? I mean, you can see it here in the hyperfine spectrum, but how could I prepare and detect the state of a nuclear spin? Well, there's a few tools that work for this. The simplest one is to tune your magnetic field to the excited state level anti-crossing, where you get nuclear spin polarization for free. How does this come up? Well, the excited state level anti-crossing, essentially it costs no energy to flip the electronic spin. And so the non-secular terms of the hyperfine interaction in the excited state can induce flip-flops between the electron spin and the nuclear spin. And so if your optics is pumping the electron spin, and the electron spin is pumping the nuclear spin, you can end up optically polarizing your nuclear spins simply by shining light on the system at this particular magnetic field. For similar reasons, different nuclear spin states can also give rise to different fluorescence levels. But this technique, it's only as good as your optical spin preparation. And perhaps more excitingly, in the last 5 years, there have been some developments of being able to actually prepare and detect nuclear spins at room temperature with extremely high fidelity. This idea was pioneered by the Harvard and Stuttgart groups in 2009 and 2010. And the idea is this. Let's suppose I was looking at the nitrogen nuclear spin of my MB center, and I could see these hyperfine lines in its ESR spectrum. If I drive this transition, what it's doing is it's rotating the electron spin only if the nuclear spin is in m sub I equals -1. And so if I send in a pi pulse on that transition, I'm executing a C naught gate, a nuclear-controlled NOT gate on the electron spin. In other words, I'm, in some sense, putting the nuclear spin information into the electron spin. And if I subsequently measure the electron spin, well, then I gain some information about the nuclear spin. And the insight of the Harvard and Stuttgart groups was that the nuclear spin doesn't necessarily get affected terribly much by this optical excitation. While it repolarizes the electron spin, it might not touch the nucleus. And so you can repeat this procedure many, 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 many times. Map the nuclear spin onto the electron spin and measure it. The nuclear spin onto the electron spin and measure it. Until you get significant statistics that allow you to actually detect the state of the nuclear spin with high fidelity and even observe quantum jumps of the nuclear spin in real time. This can lead to very high fidelity detection of the nuclear spin. I think I've seen numbers as high as 99-point-something% for a distant carbon-13. And of course, if you can prepare the spin with high fidelity, if you can measure the spin with high fidelity in a quantum non-demolition manner, you can also do preparation by measurement. And so it can be used both to prepare and to detect nuclear spins at room temperature with high fidelity. And I should add as a note that the same techniques work with resonant excitation at low temperature. Okay, so now we know more precisely how we can prepare and detect the nuclear spins, as well as what the spin structure, the Hamiltonian of the electronic and nuclear spins look like. And the next thing we should probably consider is what the coherence properties of the spins look like. That is, what are their longitudinal relaxation times? That means if you polarize the spin, how long does it take to return to thermal equilibrium? There's the T2 star time. This is the time that characterizes how long you can know the phase of a spin superposition. And then there's the T2 time, which is the decoherence time, the time that you can hold a superposition state, including Hahn echoes or dynamical decoupling. And so it would be wonderful if I could just give you those 3 numbers and we were done. But actually I can't, because they depend very sensitively on the environment of the spin. And for different samples and for different NV centers, you'll see wildly different numbers. So what causes the loss of coherence? What causes decay and dephasing? Well, one thing that causes it is phonons. Through the spin-orbit interaction, you get a spin lattice relaxation that dominates the lifetime of the spins. In addition, in many samples, you have a bath of nuclear spins to deal with. These are the carbon-13 isotopic impurities that I mentioned earlier. And these will lead to dephasing and decoherence. Worse, if you have a sample that has many paramagnetic impurities, such as nitrogen, you'll get extremely fast dephasing and decoherence. And this can also be induced by the presence of a nearby surface, which can have uncontrolled paramagnetic or electric surface states that can contribute to dephasing and loss processes. So I can't tell you just one number for each of these, and I'll take the approach of trying to talk a little bit about the coherence properties, and then I'll give you the world record numbers. But please bear in mind that this is different for every sample that you work with. Let's start with T2 star. the timescale over which you can maintain a coherent spin superposition. This is typically measured by a free induction decay, or a so-called Ramsey sequence, where you use a pi/2 pulse to create a spin superposition state. That spin superposition state then picks up a phase that depends on the detuning of your energy level from the microwaves that you apply. And that phase will accumulate for whatever the duration between the pi/2 pulses is. The second pi/2 pulse maps the phase onto a population that you can measure, and in the end what you measure is the expectation value of the exponential, the complex exponential of that phase. And if you have a situation where your energy level is fluctuating in time, however slowly, over the course of the many experiments you do to average out your signal and extract that phase, well, what you'll see is what looks like a decay with time. Now, exactly what this decay constant is depends wildly on your sample. For typical electronic grade samples of natural isotopic impurity, it's measured in microseconds, but there have been select samples in which isotopic purification has been performed, where you can see dephasing times as long as half a millisecond. Now, this is largely dominated by slow noise in the environment that leads to slow changes in your energy levels as you average many times over your experiments. And the T2 time gets at a more intrinsic decoherence time, that is, what is the noise that affects your sample during the time scale of a single experimental run. This is typically probed by Hahn echo or dynamical decoupling sequences, and this works by adding a pi pulse in the middle of the free induction decay. Essentially, again, a pi/2 pulse creates a spin superposition state, and in that first free precession period, your spin states pick up a relative phase. The pi pulse, however, inverts the effect of the environment on the spin by flipping the spin states, so that effectively, in the second free precession period, the spin is unwinding the phase that it gained in the first free precession period. And if the energy levels don't fluctuate between the first and second free precession period, then there won't be any net effect of the precession overall. And in this presence of so-called quasi-static noise, your Hahn echo will always give you unity. You won't see any decay. Of course, as you make this longer and longer and longer, eventually you'll hit the time scale of the noise. And this system, this sequence is said to decouple noise that's slower than the time scale tau. You can do even better than just this Hahn echo by adding more pi pulses in the middle, a so-called CPMG or a dynamical decoupling sequence. And again, you're in the same situation that you decouple noise that's slower than the time scale between the spin flips, but now there's more spin flips, so that time scale is faster. And by adding more and more pi pulses, you can extend the total time during which you can maintain the spin coherence out ultimately to the spin lattice relaxation time, which is set by phonons, which depends on temperature. And so indirectly, T2 also depends on temperature, with the best number that I know of anyway being measured at about 77 Kelvin in an ensemble of NV centers that showed a T2 time under dynamical decoupling with CPMG of about 580 milliseconds. Okay. And indeed, ultimately, the coherence times at the NV centers are limited by spin lattice relaxation, which depends on the temperature and also on the purity of your sample. If you look closely at this graph, you see that it ranges in time scales from about 6 milliseconds at room temperature down to as low as 200 seconds at cryogenic temperature. And it depends on whether you're working with a sample that has low paramagnetic impurities that induce cross-relaxation or high paramagnetic impurities. And this really long time scale here hints at the possibilities for coherence times at cryogenic temperatures. What about the nuclear spin? Well, just from a consideration of its gyromagnetic ratio, you might think that the nuclear spin coherence times should be 1,000 times better than the electronic spin coherence times. And that would make sense if you had a nuclear spin that experienced the same environment as the NV center. However, there's one more thing in that nuclear spin environment, and that's the NV center itself. And you might think that the nuclear spin coherence times are ultimately limited by the relaxation time of that NV center to which they're coupled. It turns out that's actually not true, because you can continuously optically illuminate the NV center, which both polarizes it and motionally averages its spin states, such that under continuous illumination, in that same sample where we had the half a millisecond electronic spin dephasing time, a nuclear spin dephasing time of half a second was observed. And I should mention the nuclear spins in diamond have, at least in bulk, relaxation times that can be measured in days. So there's really quite a bit of possibility at low temperature to get to extraordinarily long coherence times. Okay, so in my last 10 minutes or so, I'd like to say a few words about applications and research highlights. And one of the applications that's gotten a lot of press for the NV Center is quantum information science. After all, you can think about the electronic spin and nearby nuclear spins as a set of qubits that you can control, detect, prepare, both optically and with resonant microwaves. You can think of this as a small quantum register. And the time scale on which it can be manipulated is in the nanosecond for electronic spin transitions or microsecond for nuclear spin transitions. There have been a number of remarkable demonstrations of benchmarks of manipulations of the spins around a single NV center in the last few years, including things like violations of Bell's inequalities using 2 nuclear spins, demonstrations of 3-bit quantum error correction using multiple spins around the same NV center, or most recently, some very high fidelity single and 2 qubit gates that are approaching fault tolerance thresholds. Nevertheless, there's a big challenge left for quantum information science with the NV center. It's not so much the gate and readout fidelities. They need to get higher, but they're getting there. The big challenge is the number of spins that can be coherently addressed around a single NV center. Maybe you can do 5, maybe you can do 10, maybe you can do 20, but you're not going to be able to do 1 million. And so the big challenge is how to get different NV centers, different quantum registers, to interact with each other. One approach that has been taken is simply to get them close to each other. Close enough that the magnetic dipolar interactions of the 2 NV centers are stronger than the decoherence processes associated with their environment. And the Stuttgart group has demonstrated that this is indeed possible, and it's sufficiently strong if you have NV centers that are separated by a couple dozen nanometers to generate entanglement between them and even transfer it to nuclear spins. And so you might envision some array of NV centers that are capable of performing quantum information calculations. This brings me to another question, though, which is how you would resolve spins that are so close together. And indeed, there have been some remarkable developments in subwavelength imaging applied to NV centers that I should at least mention. For example, super resolution imaging using stimulated emission depletion techniques, that is, where you excite the defect with a Gaussian-shaped beam and then cause stimulated emission with a donut-shaped beam, which means that only a defect that's in that donut hole will fluoresce. This technique has been used to get really extraordinary resolutions. This is the diffraction limit. This is a STED image of the same NV center. And I think the record now is about 2.4 nanometer resolution. And I should also mention that other techniques have been developed, including those that are amenable to nanoscale spin addressing. There's another approach, too, to trying to engineer interactions between NV centers that has made a lot of progress in recent years. And that's taking advantage of the optical transitions to mediate interactions over long distances. The idea is that if you can entangle the spin state of the NV center with a state of an outgoing photon, for example, by taking advantage of the polarization selection rules under relaxation from the A2 excited state. And if you can do that for 2 NV centers and get those photons to interfere coherently on a beam splitter, then coincidence photon detection can project the 2 spins onto an entangled state and create a resource for teleportation-based gates between the NVs. And indeed, most recently, the Delft group has teleported a nuclear spin state of one NV center to the electronic spin state of another NV center, where the NVs are located on either side of a laboratory. So this is very impressive, but there's some challenges to this approach. One of the biggest of which is its efficiency. Because in order to use these photons to carry quantum information, they need to come within the zero phonon line. Any photon emitted within the phonon sideband deposits switch path information into the crystal lattice vibrations, and thus can't carry coherent quantum information. And so there's a great deal of work that's currently being done to enhance the zero phonon line collection efficiency through optoelectronic integration, that is, integrating NV centers into various nanophotonic structures, into ring resonators, into photonic crystal cavities, to try to improve the fraction of light that can be collected in the zero phonon line. Okay. So there's a lot of science that's being done with NV centers in the realm of quantum information. But we're here at the Diamond Sensing Workshop, or at least you're there, I wish I were there, at the Diamond Sensing Workshop. And that's because in some sense, in many cases, good qubits can also be very good sensors. Well, why does this come about? Consider a NV center that is in an external magnetic field. If you prepare a spin superposition of the NV center and allow it to evolve, it's going to pick up a phase with time. And the longer that you allow it to evolve, the larger a phase it can pick up from that external magnetic field, and thus the more sensitive a measurement of that magnetic field it can make. The longer it remains coherent, the more sensitive a sensor it is. I should mention, I think I forgot an over H bar there. Forgive me. Okay. So we can say something about how sensitive this measurement can be. Because if we allow our system to evolve for, say, the maximal dephasing time tau, we accumulate a phase that looks like this. Again, I forgot an H bar in this equation. And thus the minimum magnetic field that we can measure in this time would roughly correspond to a phase of 1, or a minimal magnetic field of this quantity. And so this is what our minimum magnetic field sensitivity would be in one repetition of our experiment, which clearly gets better if we can maintain our qubit superposition for longer. Of course, we might repeat the experiment many times, doing it over and over again, and then our minimum magnetic field would go down as 1 over the square root of the number of times we did the experiment. And so what's typically quoted as the sensitivity is really the magnetic field per root hertz, that is, taking into account the fact that you can do better by measuring for longer. And the sensitivity for an NV center used to measure DC magnetic fields can be roughly represented, with some constants of order unity by this quantity, where you can see the minimum magnetic field here per root overall time, times the overall time that you apply. You have a constant out front that accounts for the fact that you can't prepare and detect the spin with perfect fidelity. And then if you have many NV centers in your sensor volume, you might have an additional factor of 1 over square root of n. And so the wish list for a good sensor might include long dephasing times, excellent spin control and detection, and then high density, or conversely, good spatial resolution. So how sensitive is this actually? Under good conditions, you might get a microtesla per root hertz of sensitivity for each NV center. That means in 1 second, you could measure about a microtesla. Now that's not a very small magnetic field, but nevertheless, this is quite interesting because the spatial extent of the NV center is small. And so you can hope to obtain a sensor that has spatial resolution, while currently it's in the range of tens of nanometers. You also have the possibility for dense ensembles, as well as a sensor that is a very good material. That is, it works at many temperatures, it's not chemically reactive, it's non-toxic, it's even taken up into human cells. And so there's been a lot of growth, some of which you'll be hearing about over the next few days in this direction. But a natural question to ask centers on the fact that this DC magnetometry is limited by the time for which we can maintain a spin superposition of the NV center without any extra pi pulses. It's limited by the dephasing time T2 star. And for most samples, that's not terribly long, maybe a few microseconds. So a natural question to ask is, can you somehow access the intrinsic coherence time, the T2 time, to get even more sensitive measurements of magnetic field? So what kinds of magnetic fields would you measure if you were to apply a decoupling sequence to an NV center? Well, you wouldn't measure the DC magnetic field. That's the whole point of decoupling, to get rid of quasi-static noise. And that's because the effect of a static magnetic field in successive free precession periods is to wind and then unwind and wind and unwind. So it's going to cancel out. However, if you have a magnetic field that changes in time, and especially a magnetic field that changes in time commensurate with the time scale at which you apply these pi pulses, then you can get a net addition of phase with each free precession period. Because just as the effect of the environment flips with each pi pulse, so too does the sign of the applied magnetic field. And thus dynamical decoupling sequences are most sensitive to AC magnetic fields that are oscillating at 1 over twice the time between the pi pulses. Their frequency is 1 over 2 tau. And at the same time, it's insensitive to quasi-static noise in the environment, and so it can access the full T2 time of the NV center. How sensitive? Oh, I should mention, this is really incredibly sensitive. It's been used to measure the oscillating magnetic fields associated with nuclear spins, and most recently to image NMR signals with about 10 nanometer resolution. This by 3 groups all back to back. So how sensitive is this? You can get into the range of a few nanotesla per root hertz for a single NV center, and there have been ensemble measurements that have approached the 100 femtotesla magnetic sensitivity range. If I were to compare this to other magnetic sensors, stealing a plot from one of Christian Dagan's papers from a few years ago, I would say that in terms of the physical separation and the magnetic field sensitivity, NV centers are competitive with force sensors and doing better than Hall sensors and SQUID sensors in allowing us to combine magnetic field sensitivity with spatial resolution. And again, you'll be hearing lots about this in the week to come. So with that, I'm coming to the end of my time, and I should very briefly mention all the things I didn't have time to mention. I didn't get to the fact that there's many other types of sensors beyond magnetic field sensors, whether they be electric field, acceleration, or building a gyroscope. There's also many approaches in quantum information that I didn't have the time to discuss, whether it's coupling NV centers to mechanical resonators or to superconducting devices. And there's also a lot of things that the field hasn't gotten to yet, outstanding goals that we haven't yet achieved, including a scalable mechanism for coupling different NV centers coherently, and some outstanding goals in metrology, including things like mapping individual external nuclear spins, imaging neural activity, or attaining sensitivities comparable to atomic magnetometers. And so I'd say there's really a lot that we've done, but there's a lot left to do. And it's a very exciting time for nitrogen vacancy physics. So with that, let me thank again the organizers for this invitation. Let me thank you for your patience. Thanks.